Hi. Before we actually learn about the math of volumes of revolution, which is the next topic, I wanted to take a minute just to show you what a volume of revolution looks like. We've just spent a while talking about area under a curve and area between two curves. For instance, if I were to able to shade here, I would have this curve y equals 4 minus x squared, and the x-axis, and I could look at the area under this curve. Well, what this next unit is about is actually revolving or rotating curves around lines. It looks something like this. The area bounded by the curve and the x-axis is going to be rotated around the x-axis. And if I turn this, you can kind of see what happens, that this area, just a flat two-dimensional area, actually sweeps out a 3D volume. Now, this shape is not a circle or a sphere. It's not a rectangle, it's not a prism. It's not a cone. It's kind of the best way I can describe it is kind of like a little M&M. And that we don't have a formula for that volume. But in calculus, we're going to learn in the next couple of days, there is a way to find that volume. And that volume is based on the idea that the rotation, when you cut through the shape across the middle of it, like vertically, your cross section be a circle. Imagine a loaf of bread. If you look at just one slice, that cross section is a square, but the entire, when you stack it all up, you end up getting a loaf of bread, which is looks like a rectangle. I'm going to just take another curve here and I'm going to change it. I'm going to do the square root function. And I'm going to set that as my new function. Can only graph it from 0. Let's go from 0 to 4. And now I'm going to rotate that curve around the x-axis. And when the curve rotates again, it sweeps out this three-dimensional figure. And from the front, you can see it kind of rotating around there. And this entire shape will have a volume. And when I'm sweeping it out, what you're seeing right now is simply the what's called the wireframe. If I switch it to a solid, what ends up happening is you get a little bit more of a view that this whole thing is a solid shape. Now, this does have a hole in the middle, but our shapes will not. We'll be rotating the line and creating a solid object. Okay, so I want to just show you some other pictures. I'm going to go to this one. And here's another example. This is the square root of x again, and I'm just going to pull the end out a little bit. Seems not to be working, but it'll work in a minute. And now what I'll do is I'll rotate the curve around the x-axis. When I rotate that curve, this little piece right here, I usually call it a slice. Some people call it a cross section. Let's rotate that around again. That cross section is a circle. You see that right there? And if we think about all the circles from left to right, all these little slices. Oops, okay. I'll cancel that. Look at all these circles. Each of those circles has an area, pi r squared. But if we add up all those areas as if we were stacking them, we get the entire volume. This is called the disk method, where you rotate a curve and that curve creates a shape where the cross-sectional volume is a circle. Now, the other thing to know about this, the important thing to remember is that what you end up having, if I go back just to my functions, if I clear my graph, and I'll go back to this 4 minus x squared. I'll go from -2 to 2 again. The important thing for a disk is that the axis of revolution, in this case the x-axis, is one of the boundary lines. That is the way you tell that you're going to be able to use the disk method. You're doing something called revolving or rotating, and one of the boundary lines is the x-axis. Now, along with the disk method, which we're going to spend 2 days on, we're also going to talk about the washer method. And this is the washer method. This time, the area is bounded by 2 functions, sometimes 2 curves, sometimes a curve and a line. And when we rotate it around, I'm going to show you what happens when I rotate, let's say, this slice, and you're going to hear me say that a lot, a slice or a cross section. Let's rotate this around the x-axis. And, there's our circle, just like before. But what if we move over here? Now look over to the right. I'm going to rotate this around. And I still have a circle, but the circle has a hole in the middle. So pi r squared is no longer the area, because we have to take the area of the whole thing and subtract the area of the inside. When you have a shape that looks like this, again, it's called the washer method. When you have the washer method and you have this hole, it's very similar to the disk method, but there's a small change, and I'm going to show that to you tomorrow. Now, what I'm going to do is I'm going to go back here and show you what happens when I rotate a whole lot of rectangles. Let's see if I can make a lot more. And then move that all over. Okay, now look over to the right. When you rotate this whole thing around, you get this shape. Oh, I'm going to show the surface now. When I rotate that around, I get this shape that in certain parts has a hole in the middle. And again, that hole is easier to see when I look at just one rectangle. Let me take away the surface. Let me rotate it around again. There it is. The important thing for a washer is that the boundary line, or let's say the axis of rotation, whatever you go around, is not a boundary line. And that's how you tell the difference. For the disk method, when you rotate, and rotate this around the x-axis, and I'm going to do this one more time, the area bounded is this area right here, the area between the function and the x-axis, and I am rotating it around the x-axis. Even if I pull the axis down a little bit, I used to be able to do this. I think this might not be working now. Oh, there it is. And when I rotate around, here's the circle again. Now, this is a little, there we go. See? So as long as my boundary line is an axis of rotation, that will create a disk. But if my boundary line is not an axis of rotation, it creates the washer, which has a hole in the middle. Okay? So I just want you to have an idea of what this all is going to look like. Because tomorrow we're going to go straight to how to handle it mathematically. I will see you in class. Bye-bye.